dings. There we go. Okay, so while you're working on number 1 and number 2 for this warm-up, you have until 9:30, so there's about 3 minutes left for you to try this, and I want you to keep trying until you get it. Just a heads up, it looks like, yeah, we should be wrapping up this unit today. I think I'm just gonna cover a couple of like more techniques for integrals, and that's gonna be it for this unit. That means then that your test is going to be next week. I think we're gonna have your test on April 29th. I know that I said we're wrapping up today, and you know, some of you are like, why don't we just take the test on April 27th, right? Because you guys are all eager to get this done, right, and move on, right? But no, I think we should review not only on Monday, but also on Tuesday. Integrals are very difficult, and it's something that we should definitely practice more together. So I'm thinking we'll finish up today. I'll give you your study guide, your review, your other stuff. Oh, juniors have SBAC testing on the 29th? Oh, it looks like we just have to do it on the 27th then, don't we? That might have to be the case. I think we might have to just have your test on the 27th if you have SBAC testing. Of next Tuesday? 29th of next Tuesday? I mean the Thursday? No, the test. Yeah. I think we might have to do the test on the 27th. I can't push it further into the following week. Come in office hours? For what, Brian? No, about the test. For the test. You think we can just hold it on this day and then you guys want to come in during office hours to take? That's a lot of testing. You're going to do the SBAC testing and then do the Calc test? You sure you want to do that? That's a lot. But I guess it would be better. I guess it would be better than taking the my test sooner. No, that's too much. I don't think to give everyone more time. No. That throws a monkey wrench in there. All right. I think I'm going to be a little bit lenient on this one. Oh, this is a tough one. Shoot. The SBAC is going to eat that up. Huh. I don't want to give the test on that Tuesday. That's too soon. I can't give the test on Thursday. The seniors would be able to take it, but then the juniors won't be able to. When can the juniors make it up? Knock me. What's the plan here? Knock me. What is the plan here? What about on Friday office hours? I don't know. Yeah, I mean, you could do office hours on Thursday as well, and you can do office hours on Friday as well. I think that has to be the case. It's just I don't want, that sucks. I don't want you to have to like force yourself to do something after class, but I don't see any other way. All right, we'll figure something out for the juniors. So yeah, we'll just hold that test date anyways on the 29th. Juniors, you will be exempt because you're taking the SBAC, but you will have to do a makeup. I just got to figure out a day that's going to be there. The SBAC is both days. Oh my God. You think I would know this being your math teacher? You're right. I do know this. I actually got this email and I was looking at it and I was like, I don't have any. I forgot there's juniors in my AB class. Okay, we'll figure this out. Juniors, yeah, we'll figure this out. Yeah, you're gonna be drained. I don't think that's a good idea either, because then you won't be going into this test well prepared. I'm gonna have to open up the test window for you guys at some point on. I'll figure it out. We're gonna set up I think I'm just have to set up a date where you're gonna do it off of regular any hours, like not after during my office hours, not during then. It might have to be over the weekend. I think I might just set it up that way so you guys can open it up and do it sometime over Saturday and Sunday. Yeah, we're just gonna have to do it that way. So I'm thinking that for you juniors, I'll have it set up for you guys open over the weekend. It'll be timed still. You just won't be monitored by me. You just have to go in there and take it timed. Yeah, we'll figure that out. All right, that's good to know. Okay. Either way, we'll wrap this up today. We're going to go ahead and start reviewing, and then I'll assign your delta math work for your, curve, and your review sheet for your curve. And for those of you who are wondering, I still need to curve your last test. Just been too lazy. I have all your scores. I just got to key them into a spreadsheet, and it's really annoying to do. So once I key them into the spreadsheet, the calculations can go pretty quick. But yeah, I just got to key them into the spreadsheet and get them on there. Is there going to be delta math for this one? Of course, Brian. There will be a delta math for this one. I'll put it up at the end of lecture today. Yeah, I'll put it up at the end of lecture today for you to work on it. And then also the homework that's there, the study guide that's a worksheet as well for you to get that curve. All right, so let's go ahead and take a look at some of your responses here for number one. Okay, so let's go ahead and let me open this up in a new tab. And let's go ahead and take a look at some of these answers. Let's take a look at some of these answers. So for number one, right? We got an attempt here. I like this attempt. This is looking like they're using the power rule, but they understand that an e to the x power, right, an exponential function repeats itself when you take the derivative, which looks like it should be right. But then if we were to take the derivative of e of this, you have to do the quotient rule, because now you have a function of x in the denominator, and when you do the quotient rule, you know it gets really messy, and it's probably not going to look like that. So this is close in the idea that you have, but it doesn't take that whole 3x plus 2. It doesn't take that whole 3x plus 2. So that's a good attempt. This person was thinking, I might need to use a U-substitution, which is a good thing to think about. It is going to be a U-substitution problem. The only issue is, if you let u equal to this whole thing, that might work, but then you see when you replace, would that work? Could you do this? Put this in here, that cancels that out, and you end up with the integral of du. No, because the derivative of this is not this. This is showing that du is equal to e to the 3x plus 1. Don't forget the chain rule. You got to take the derivative of 3x plus 1, right? Derivative of the inside is 3. That needs to be multiplied with that. So there should be a factor of 3 here, which would have been, actually, it would have been okay if you had that factor of 3 here, and then you would put here 1 du over 3 is what it would have became. You were very close. You're very close. Very close. I like that attempt. Rewriting it. Rewriting it there. This one is blank. This one, that's a good U substitution right there. U is equal to 3x plus 1. Du then is going to equal to the derivative of 3x, right? I might have caught you in the middle of writing it there. And you're so close. You have the right idea. Chain rule is going to be in that case, but the derivative of e to the x would be e to the x. It would not go back to e to the 3x plus 1. So that 3x plus 1 is definitely going to be up there in the power. It's definitely going to be up there in the power. This person went straight to number 2 and did it on this slide. I'm sorry. I should have shown you that slide 2 had the problem there, so you didn't have to squeeze it all into one slide. So sorry about that, whoever is doing number 2 on this slide, which is fine. Also, I don't think you noticed, but number 2, that was x squared. But if it wasn't x squared, that's beautiful. If it was 1 over 1 plus x, this is the correct way of doing it, or what you have. I'm sorry, I didn't mean to rain on your parade. It does look beautiful though, and your work is elegantly done. Except this part is not. It's not the integral of uv. The u is going to go in the bottom. It's going to be 1 over u. It's going to be 1 over u. Oh God, I'm sorry. I'm just going to scroll on. I mean to keep messing with you there. This one, that is the right answer. 1 over 3 e to the 3x plus 1. Because of the chain rule. If you take the derivative of this, the derivative of 3x is going to be 3. The 3 will cancel with the 1/3, and that will get you back to the original problem. Some people some people, when they see the exponential function enough, they know the integral of it by heart. And it's kind of interesting when they do that, but not everybody does. You're almost there. Just put this over a 3 plus c, and then you're done. That's a line. All right. So check this out. We know, right, as a side note, we know that the integral of e to the x dx is equal to e to the x plus c. That's perfectly done. That's well and good. That's all nice if it's just a single x. This is not a single x. This is some stuff that's there. That's too much stuff, right? It's too much stuff. So we try U-substitution for this one. So we go ahead and let u equal to 3x plus 1. Now, when you do that, you end up with this problem here, right? You end up with the integral of e to the u, right? Which looks close enough to this, but we need to make sure that this differential matches with the variable that we're dealing with. So right now it's e to the u dx, and that's not okay. I can't integrate this. I need those variables to match, that variable up there along with this differential here. So for us to do that, we go ahead and take the derivative of u here, and we find du is equal to 3. The derivative of 3x is 3 dx. Solve for dx by, well, getting it alone. And I can replace this right here, this dx, with du over 3. And then when I do that, I end up with this new integral, the integral of e to the u du over 3. That over 3 is just a fraction, right? And I can move that over and rewrite this as the integral of e to the u du times 1/3. And that 1/3, of course, I'm just going to move it to the front, right? That's all that over 3 is. It's just 1/3 times du. Take the 1/3 out, move that out to the front as a constant, and then integrate what you have here. And you see this integral right here, integral of e to the u du, looks exactly like this right here, except instead of x's, it's u's. So I'm going to go ahead and integrate this. This is going to become 1/3 e to the u plus c. I don't need the parentheses. What am I doing? I could just write this out. E to the u plus c. But we also know that u is equal to 3x plus 1. So this is going to be equal to 1/3 e to the 3x plus 1 plus c. And that is my answer. Again, this is just something that takes practice. There's some students who have been coming to my office hours and practicing these U-substitution problems from the homework. And I'm telling you right now, I'm able to see them evolve from not knowing how to start a problem to going all the way to the finish line with it. And it's awesome to see. And that's all it is for these integrals. It just takes practice. And then the beauty of these problems is you can double check if you did this right just by taking the derivative of this. If you take the derivative of this, you should get back to what you had, right? If I take the derivative of this whole entire thing with respect to x, I would see that this is going to come out to be 1/3. The derivative of an e to the x function is going to be itself multiplied by the derivative of the inside function, and the derivative of 3x plus 1 is 3. Derivative of c is a constant, which is just going to be plus 0. Simplify this out, 1/3 and a 3 goes away, and I'm left with e to the 3x plus 1, which is the original problem. So that's right there is how you can double check it. That's for all these integral problems. We have a way of double checking it just by taking the derivative of it. Now, do you have to always do that? No, but you have that option. All right, so that's that problem in a nutshell right there, right? I'll give you guys a second to take a look at that, copy it down. Hopefully you got it. If not, it's posted on your OneNote. You can go look at it right now. It should be loaded by now. I'm going to go ahead and take a look at the next responses, which is number 2. I want to see some of your responses here. Let's see what we got here. We got a blank, and we got someone who just wrote down the inverse tangent of x with nothing else, and that is correct. This is the inverse tangent, or the arctangent, right? That's all it is. And it's one of those things that you need to be able to recognize. Another student with the inverse tangent spelled out. If you want to be lazy like me, you can just write down arctangent, A-R-C tangent. Tangent -1, it's good. I'm assuming that's the inverse tangent. And shock face and arc tangent is being written out right there. Good, 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 good. Yeah, that's all it is. You don't need to do any U-substitution for this one, right? You could try, but then the problem is you'll get 2x, and there's no 2x's there, right, for that U-substitution. When you do U-substitution, you need to look for a factor that looks like a derivative of the other function. You have to look for a function, not a factor. You have to look for a function that looks like it's a derivative of the other function, right? And this one, there's no 2x's there. So yeah, the answer for this, This is just going to be the arc tangent of x plus c. And that's it. I promised I was going to upload the picture that I found online of the integrals and the derivatives, which was this one right here. And I'll be honest with you, I haven't uploaded it yet just because I'm like so hesitant to upload it because there's just some of them that, I guess I should. But honestly, I honestly, I don't think this one is ever going to show up. This one, or this one are going to show up for, or this one, as a matter of fact. Sine, inverse, tangent. Yeah, those ones I don't see ever showing up. So I guess I could just put the x's on here, save this, and upload that. But yeah, why don't I just do that, Knock Me? I don't know, Knock Me. Yeah, let's just save that. Is that a save? Save a copy? Save a copy. Okay, yeah, I'll upload this. What am I doing? I should just upload it. But then again, you guys could have just Googled this and have your own copy of this, I believe. But yeah, that's going to be the case. So if you look here, bam, the integral of tangent of x. Wait, that's not what I'm looking at. Hello, Knock Me. This is the one we're looking at. The integral of 1 over 1 plus x squared dx is equal to the inverse tangent of x plus c. And it's just one that you need to know, one of the three inverse tangents. I know that, I'm sorry, inverse trig functions. There's inverse cosine, but you don't need to know that one because inverse sine is actually one that it's a long way of saying it. They mostly do the inverse sine function when they're dealing with integrals. Inverse cosine looks very similar to it, except it has a minus sign, if I remember correctly, when you do the derivative, right? Right? The derivative of arc cosine, if I remember correctly, is not written in here. Hello? Interesting. They don't even look at the derivative of the arc cosine. Anyways, that's that. Now, here's the thing, though. Some of you guys might notice, I don't know if you see this or not, but this is all well and good if it's 1 plus x squared, right? But there's a cheat sheet over here. What happens if it's not 1 plus x squared? What if it instead is another number plus x squared, but it looks like it follows that pattern? Well, it's actually just this then, isn't it? It's just 1 over a times the arctangent of x over a. So how does that work? So let's do that today. Well, by the way, if you want to label your notes for today, this is going to be titled Techniques for Integration. There are additional techniques on top of U-Substitution if U-Substitution doesn't work, or if there's like little tricks and whatnot that you need to try to apply to the problem. So we have this right here, right, as our answer for that one right there. Let's say we have an example here that looks like this instead. Let's say I have here instead, let's go with the integral of 1 over 2 plus 9x squared dx. Now, this up here only works if it's in the form of 1 over something squared plus something squared, right? And you'll look right here. This down here doesn't look like it seems to be in that case, but we can actually force it to be in that case as long as our x term has something squared. The numbers you can deal with on the side. You can just kind of like force it to be something, and when you square it, you get that number. X is on the other hand, if I have x that's not being squared, this won't work out. So if it's 1 over 2 plus 9x, then that would be a U-substitution problem. All right, I'll show you once we go into here. So check this out. If you look here, let's call this up here. We call it like let's call it U this time, right? Let's call that U. And then over here, let's call that A as a constant. Okay. If we look at this closely, right? If we look at this closely, this U right here is going to be equal to 9x squared, right? In other words, it's not. I'm sorry, it's not just U. It's U squared, I should say. That's going to be an easier thing to see because I'm trying to figure out what U is, right? So if U is equal to 9x squared, can you guys see that U itself is going to equal to 3x? Because 3 squared is equal to 9, x squared is equal to x. So U in this particular problem is going to equal to 3x. That's going to be a little bit easier to deal with. Now over here, I'm going to see that A, right? A squared is equal to 2, right? That's this part right there. I don't want A squared though, I want A, because if you look, right, the equation for this is 1 over a times the arctangent of x over a. So when we come over here, a is going to equal to the square root of 2. A is going to equal to the square root of 2. Okay? All right. Now that I have my a and I have my u, and I know, right? I know that let's put this on the side right here, this note right here. I know that the integral of 1 over a squared, I don't know, I just put it up here. The integral of 1 over a squared plus u squared du, it's going to equal to 1 over a times the arctangent of x over a plus c. Once you have your a and you have your, not me, keep your variables the same. If you're going to put u's, you're going to put u's. If you're going to put x's, you're going to put x's, okay? All right, not me. All right, so I have here, that's going to be my answer for this one. So if I know what my a is and I know what my u is, the integral of this thing right here, right, is going to look like this. It's going to look like the integral of 1 over the square root of 2 squared plus 3x quantity squared dx. You don't need to show this step, by the way. You can go straight from here to my next part right here, which is going to be the answer. This is going to equal to 1 over the square root of 2 times the arctangent of, in this case, it would be u over a, but our u in this case is 3x over square root of 2 plus c. And that's our answer. And that's our answer. So you're going to need to do a little bit of manipulation to get it to fit into these. I'm gonna put this back up here. Give me 1 second. You're going to need to do a little bit of manipulation. So you got to keep an eye out for these patterns right here. Arcsine, arctangent, arcsecant are very like arcsine and arctangent are very common on the AP exam. Arcsecant has shown up like once out of like 5 or 6 tests, and all the other arcs don't even bother. But inverse sine, inverse tangent are ones that are pretty common. So you need to keep an eye out for these patterns right here. If you have 1 over a squared plus a squared, and you're doing the integral of that, it's going to look like an arctangent problem. You just need to rearrange the squares and find out what the a is and what the x is. And the other option is that they'll have it under a square root, and you'll have the square root of something squared minus something squared. If you can get that down, you can figure that out and rewrite it as the inverse of sine, right? The integral of the inverse of, the answer would be arcsine of x over a. So the tangent one has a 1 over a in front. The sine does not. It just has x over a inside. You just have to figure out what that is. So the easy way of looking at it is if it was just a 1 minus x squared, but hopefully you understand 1 is 1 squared, right? So your a in this case is 1. So that's why it's x over 1. It follows that pattern right there. But yeah, that's just something to keep in mind when you start coming across these problems here. And I think what's alarming for some students is they'll see something like this and just like kind of wonder like, well, do I need to do U-substitution first to try to figure it out? And if U-substitution doesn't work, what am I doing to do next? It's a long list of trial and error until you find out what it should be, because I'll show you this right now. If this problem just changes a little bit, if I just gave you a problem like this, 1 over 2 plus 9x dx, that doesn't follow the arctangent version. And you'll say, why not, knock me? Why can't I just do that? Because look, a here is still equal to square root of 2, right? But in this case, u here is going to equal to 3 times the square root of x. And this right here, that screws you over. You can't integrate this using the arctangent and then throw a square root in there, because then when you take the derivative of it, you have to remember, you have to take the derivative of you have to chain rule it, right? If I try to do it this way and I say my answer is 1 over the square root of 2 times the arctangent of 3 times the square root of x over the square root of 2, you'll say, knock me, that looks perfectly fine, but it's not. It's not okay, because when you take the derivative of this to double check if it matches with your original answer, it doesn't match up, because you have to chain rule this. You have to chain rule this. And when you chain rule that, it messes up the problem. And you'll say, knock me, you didn't chain rule this guy. And that's the thing. It actually does chain rule it. It's just somewhere else, and I can't show you that work right now. How'd you get that for u? Oh, sorry. Sorry. I should show all the work. U squared is equal to 9x, right? Because I'm thinking it follows this pattern. But then u would be equal to 3 times the square root of x, because I have to square root both sides. Does that make sense, Monica? Does that show it? Is that okay? I think that's okay, right? That's where I got that u from. Yeah, okay. So yeah, so that's where it kind of messes up, because here it's just x to the first power, right? And you can just constant rule it. This one becomes x to the 1/2 power, and that just messes up this whole thing. So this is not an arctangent problem anymore, just because the x is not a factored or a squared form of that. So it kind of messes it up. So for this problem, I can't do this because that doesn't work. What I'm going to do instead, right, is another method. I just try something else. Okay, arctangent doesn't work. Another method I've learned, U-substitution. Try let u equal to 2 plus 9x. And I get over here, du is equal to 9 dx. I don't know if you guys saw that I don't know what happened with my writing there. So I have over here, du over 9 is equal to dx. I have a method here of substituting out this with u. And I have a method of substituting this with dx. So I end up with a new problem here, 1 over u times du over 9. And then right here, this becomes a nice problem of, okay, the 1 over 9, I could write that in front, times the integral of 1 over u du. The integral of 1 over u is the same thing as the integral, I don't know why I erased that, is the same thing as the integral of u to the negative 1 du, which we all know now at this point, the integral of u to the negative 1 power is going to be the same thing as ln of u plus c. And then we just replace that u with 1 over 9 times the ln of 2. I don't need parentheses. It's already inside the absolute value. 2 plus 9x plus c. So I know that's like, what the heck is he doing here? I hope I'm not going too fast, but that is the U-substitution that we've learned in the past, and it's just something that you got to see. Sometimes you use U-substitution. Sometimes it looks like you're going to use U-substitution, but it's just going to be another integral that you need to know. Yeah. And how do you know? It just takes practice. Honestly, I can't stress that enough. You practice, practice, practice. If you haven't started doing the homework yet, now's the time to start doing the homework. The U-substitution one's a good homework practice to start doing these integrals. And then, of course, it applies into the other section, which is the differential equations, where you have like the dy dx's and whatnot, and then you integrate both sides, but you have to know how to integrate both sides. So that's why today I'm going to be covering a couple more techniques of integrating different functions. Okay, so hopefully you guys got that down. Hopefully. There's little knickknacks and tricks along the way here. Some of them are a little bit stranger than others. Let me show you another one here. All right. Yeah, let's do another one. Let's take a look here. So in the homework, some of you might have come across a problem that looks like this. It'll be the integral of cosine of x times sine of x dx. Right? And if you've been practicing your use substitution, you will realize that one of these functions is the derivative of the other function. Right? So right off the bat, we know, right, there's no property where you can just take the antiderivative of cosine and multiply it with the antiderivative of sine. It doesn't work that way. There's no product property for integrals. Unlike derivatives, there is a product property for derivatives, but there's no product property for integrals yet that we know of, right? So when I look at this, I can't just integrate, oh, the antiderivative of cosine is negative sine, sine. The antiderivative of sine is negative cosine. It doesn't work that way. I can't just multiply them together. I just have to try different techniques. And there's nothing here that looks like that, but I could do U-substitution because I do notice that the derivative of sine is cosine, right? So I could let u equal to sine of x. That means that du is going to equal to cosine of x dx, right? So du is over cosine of x is going to equal to dx. And I have a method of doing this integral, right? I have here the integral of cosine of x. Replace the u with sine of x. I'm sorry, replace sine of x with u. and then replace the dx with du over cosine. What's going to happen here? What's going to happen here? Am I doing this right, guys? Is this working along okay? Cosine cancels out. I'm here with the integral of u du. Is that looking right? Cosine cancels out. Yeah? Good, good, good. Take the integral of both sides and end up with u to the second power over 2 plus c. But instead of u, this is going to equal to sine of x squared over 2 plus c. And that's my answer. So here's the thing. I didn't see this last year because there was only like 2 problems on the AP exam. But in the past, one of the weird jokes that they like to do with these integral problems is they love giving you problems with trig identities. And it bothers me a little bit because not everybody's very strong with trig. Not everybody's strong with trig. Now, this one's an easy one to look at. This one's not too bad, right? This one is just kind of like, if you're asking me, like it's not too bad. Like, you know the derivative of sine is cosine, you know the derivative of cosine is sine, and you can work your way through it and you're okay with it. You know? At least I hope you're okay with it. It's not that bad to deal with. What's annoying though is if they come across problems that involve trig identities and you have to do a little bit of algebra. I say it's algebra, it's pre-calc level algebra, right? It's algebra with pre-calculus things, and simplify it, and then you'll be able to integrate it easily. So this one, right, hopefully you see, like, okay, it's set up nice and good. But check this out. Sometimes they like to play these weird jokes on you, and I'll show you one right here. I call it a joke, but it's just a they like to put it's a clever problem. You ready for this? Take a look at this one. Let's say I have here the integral of the square root of 1 minus sine squared of x dx. The square root of 1 minus sine squared dx. Now you'll say, I have no idea how to do that, right? Or actually, I shouldn't say that. You know what? Anyone? I kind of gave it away. I was saying, like, this problem isn't that bad. This problem isn't that bad, but it looks terrible. But you know what? I should have a little more confidence in you guys. Does anyone know? And I kind of said it earlier. It involves trig identities. Does anyone see this problem and have an idea of how they should attack it? Because I'll be honest with you right now, U-substitution is not going to work. There's no cosine there, right? I can't let u equal to sine because the derivative of sine would be cosine, and there's no cosine there to cancel out. So that doesn't work. I can't let x equal to u because then I'm going to be stuck in the same problem, because then I'll have sine of squared of u, and it's still 1 minus that in a square root. So U-substitution doesn't work here. U-substitution does not work here. Right? There's nothing else to sub with. There's no other functions there. Right? So, and does anyone have any ideas before we actually go on into actually doing this problem? Does anyone know any trig identities? That's the main hint I'm giving here. Does anyone know any trig identities? And it's okay if you don't, but I just need to double check. Because I don't know if they got into trig identities last year with you. I doubt it because there was no time. Arcsine. Arcsine is equal to the inverse sine function, but I can't just, what would you want to do with that arcsine? We can't just replace sine with arcsine, right? I can't replace addition with subtraction. So that's the idea. Arcsine is the inverse of sine, and you can't just replace a function with its inverse that way. So that's a good look, though. 1 over cosine of u. What does 1 over cosine of u look like, right? 1 over cosine is the same thing. So that's not a bad start, right? 1 over cosine, right, is 1 over cosine is the same thing as secant, though. That's the same thing as secant, not a sine. So that is an identity. That is an identity, but it doesn't work out. Arcsine and arccosine, again, those don't actually, do you know of a relationship between arc sine and arc cosine with this? Because first of all, some of you guys might be looking at like the integral of 1 over this. This is not the integral of 1 over this. This is not an arc inverse. I'm sorry, an arc integral, right? I can't, it's not 1 over. It's just this right here. So cosecant squared, remember cosecant is equal to, I guess you could replace that with that. You'll get 1 minus 1 over cosecant squared. That is an identity. That is a valid identity. That is a valid identity. But does that help you to do this integral? It's not bad though. That this is true, Brian. That is a true identity, and that does right into there. But I don't know if that helps me to take the integral of this. I don't know what the integral of the square root of 1 minus 1 over cosecant is, but that is a true thing. But I don't think that's going to work out for us. So that is another one. That is true, right? Sine of x does equal to 1 over cosecant. You are correct on that one. That is a true identity, but it's not an identity that helps us. All right, I'm just going to help you guys out. There are a bunch of identities that kind of show up in the trig world, but there's one, I should say one. There's about 2 or 3 trig identities that run prominent in AP Calc. And what I mean is they show up quite often in here. And the first one up is this identity. Sine squared of x plus cosine squared of x is equal to 1. This is the Pythagorean identity for trig functions. Have you guys seen this before? Have you ever seen sine squared plus cosine squared equaling to 1? Monica's saying yes. And here's the thing. You might look at this and say that doesn't look like that. Prepare to be annoyed. If I subtract sine squared of x to both sides, guess what I end up with? You'll end up with cosine squared of x is equal to 1 minus sine squared of x. So here's my kicker. What do you think I can replace 1 minus sine squared of x with? What can I replace 1 minus sine squared of x with? Anyone? Any ideas? Cosine squared. So I'll end up with the integral of the square root of cosine of x squared dx. You ready to get even more annoyed? Right, because I replaced it with this, right? The square root of a square cancel each other out, and I'm left with the integral of cosine of x. Would you guys agree? If I have a square root of something squared, those guys cancel out. So I'm left with just the integral of cosine, which happens to be sine of x plus c. You frustrated yet? You annoyed? I know when I learned this stuff, I was super annoyed. It made sense afterwards, but during it, I was just like, what kind of black magic nonsense that you can just, go through to hell? And then, yeah, eventually I've just come to accept it. There are a lot of problems that look like this, and I got super annoyed. I kid you not, there was one problem. I still remember to this day. I learned, just so you get an idea of when I learned this, I learned AP Calc in high school in 2001, 2002. It's been 20 years. God, I'm old. It just hit me right there. But here's the ignore that crazy timeline part. I still remember this problem to this day of how annoyed I was when I saw it. The integral problem that I dealt with, you know what the technique that showed up for that one was? The technique was to add tangent to the problem and subtract tangent to the problem. And it comes from this idea of rewriting a problem. So, if you add tangent and you subtract tangent, right, you technically don't add anything to the problem, right? So when you add tangent and you subtract tangent, it's not doing anything to it. But if you were to rearrange it with the rest of the problem, there was like a square root involved and some other stuff, it's somehow turned into an integral problem that you could do. And I remember looking at the teacher and just asking him, how would I have known that I needed to add tangent to the problem and subtract tangent? And he looked at me straight faced and was just like, you don't. How am I supposed to do this problem then if that's the only way to do this one? And he's just saying like, there's going to be a bunch of trig function problems, and there's no way to memorize all those, like to memorize like, hey, I need to, do this, do this, do this. It basically comes down to, do you know your trig identities or not? And I was so mad, so mad. But anyways, I'm going to give you a couple of pointers right here. We're not going to go through all of them, but I'm going to give you a couple of pointers, and it's a couple of shortcuts I've found on the internet for trig functions when you're dealing with them with integrals. So here is the first one. It's a lot, so I'm going to pause here and give you guys a chance to write this down. If you have the integral of sine to a power times cosine to a power dx, and you're not even looking at square roots, you just have something that deals with this. One technique is to rewrite them in forms of the other. So in fact, if sine is being raised to an odd power, split off a single sine, rewrite the remaining signs in terms of cosines using this identity, sine of x equaling to 1 minus cosine. If it's the other case, if n is an odd integer, split off one single cosine, and write the remaining cosines in terms of 1 minus sines. Now you're like, what? I know, I was the same way. After you do, and then if you can't do that, if both of them are even, use a power reduction formula, which is, again, I hate this thing because then it's another thing that you need to memorize in order to do. But it's just, I feel it's unfair. It's like, they shouldn't be asking that from you to memorize this, but it's just one of those things that AP Calc assumes that you know everything math related before it. And I hate the fact that, they shouldn't be testing you on whether or not you remember this power reduction formula, but it's fair game. It's one of those things that it might show up. It might show up and it might not. Okay. Let's see here. I want to show you a problem with this. Okay, let's take a look here. You ready? Hate this so much. So take a look at this example while you guys are writing this down. So let's say I have here the integral, right? The integral of, what's a good one? Let's go with cosine to the third power of 4x. Okay, no signs involved, just cosine itself to the third power. All right, I can't do U-substitution here because if I just straight up do U-substitution, if I let u equal to cosine of 4x, du is going to equal to sine, negative 4 sine of 4x dx. And you look there, there's no signs to replace that with, right? There's no signs to replace that with. So that doesn't really work out for me, right? So here's what this is saying. Cosine is to an odd power. You see that? The power of my cosine is raised to an odd power. So are you ready for this? The technique that this is telling us to do is to rewrite this as the integral of cosine of x times cosine squared of 4x. So the remaining cosine is going to be written in terms of 1 minus sine. So I'm going to take this right here, and rewrite this. So this right here is going to now become, right, the integral of cosine of x times 1 minus sine squared of x. Wait, hold up, I messed up. Sorry, 4x. That is very important. You can't just magically make those 4s disappear, knock me. Ooh, good. All right. Now, do you see the technique, why we do this? Remember, when you're dealing with sine and cosine and you want to use U-substitution, you need to have the other trig function there, right? So if I do the derivative of sine, cosine is there to get canceled out. If I do the derivative of cosine, sine needs to be there for me to cancel out. Now that I've rewritten this, right? Now that I've rewritten this, hopefully you can see it. Here's a sine function. It's not going to cancel out as easy though because there's a 1 minus it. So that's not going to work out too well. But this cosine, that cosine's nice and alone. And it can be canceled out fairly easy by another cosine. There's no ones involved, no 1 minus cosine, it's just cosine. So for this problem, I'm going to let u equal to sine of 4x. Now you'll say, knock me, why didn't you let it equal to 1 minus that whole thing? And you can. It's just the only problem is you'll have a sine squared, and if you chain rule that, you're going to need not only a cosine to cancel out, but another sine, and I don't have another sine there to cancel out. So I'm just going to let sine, u equal to just sine of 4x by itself. So I'm just going to replace this sine right there. I end up here with du is equal to 4, right? Derivative of 4x is 4. Derivative of sine is cosine of 4x dx. So over here, I end up with du over 4 cosine of 4x dx. And here we go. Now I have it set up. I go ahead and take a look here. Dx can be, oh, knock me. Hello, where are your dx at? There it is. So I'm going to go ahead and replace, right, dx with this. And I'm going to go ahead and replace sine with u. So check this out. This is how it's going to look like. I'm going to have here the integral of cosine of 4x times 1 minus u squared, because it's sine of 4x is what u is going to be replacing with, times dx, which is going to be du over 4 cosine of 4x. Now check this out. That cosine of 4x right there is going to cancel out with that cosine of 4x right there. And if I rewrite this whole thing, this is going to become, you ready? 1 minus u squared times du over 4. du over 4 is the same thing as 1 over 4. I can put that out in front. I can rewrite this as 1 over 4 times the integral of 1 minus u squared du. That's an easy integral to deal with because the integral of 1 is just u. Integral of u squared is going to be the power rule. So I'm going to have here 1 over 4 times u minus u to the third over 3, right? Plus c. So all this said and done, I'm going to end up with 1 over 4. U, of course, is equal to sine of 4x minus sine of 4x to the third power over 3 plus c. And that's that problem in a nutshell. It looks more complicated than it is. And that's the part that I think I hold a grudge with the most. All these problems look crazy. If you were to show this to a person who was not studying calculus, they'd be like, wow, you're ridiculously smart. I have no idea what's going on there. But if you looked at it piece by piece, you realize it's not that complicated. It's not that great. It's honestly a magic trick hidden inside this math problem. The only thing is you just need to know what you're looking for when you're dealing with something that looks like that cosine cubed right there. And like I said, that cheat sheet right there would be nice. Where'd the first u inside the brackets come from? The first u inside the brackets here? U minus u cubed over 3? Brian, is that what you're asking for? Yes? If I have the integral of 1 minus x squared dx, right? You do this piece by piece. So this is the integral of 1 dx minus the integral of x squared dx. The integral of 1 dx, right, is going to be x, because the derivative of x would be equal to 1. Minus x squared, the integral of x squared would be x to the 2 plus 1, right, because that's the power rule, divided by 2 plus 1. Okay? So this right here, that's where that u comes from. The integral of 1 is equal to u, right? That's this guy. Let me give that another color here. That's where this is coming into play. And then this one right here, the u over u to the third over 3, that's the power rule on the integral. Yeah, so that's where those guys came from. So it's like a combination of everything that we've learned along with a combination of everything that you learned in your previous classes. So fun times, guys, fun times. Okay? All right. Yeah. So that's that one. I got another one that is a shortcut like this. I'm going to put them on there, and then you guys can go ahead and copy them down as well. I'm going to just put this. Do you guys have this copied down? Actually, here, I'll put this down first, and then you guys can copy that later. Copy this problem down first, and then I'll put up the remaining cheat sheet. But yeah, get that copied down. Will we have a problem like this on the test? Yeah. Yeah. Wait, hold on. Let me actually double check. I'm saying yeah very confidently, but I actually don't know. Let me look at the test real quick. Don't look at this real quick. That's your test. You didn't see that. Let me double check. Let me double check. You will have one problem like this. Just one. You know what? No. You know what? I make your tests. You know what? I make your test. I'm not going to put that on there. Yeah, no. Instead, it will be. No, I don't want to rob you of your chance to score points on that. All right. We'll figure it out. I'll figure it out later. All right. Anyways. Yeah. You put me in a tough situation, Monica. I kind of don't want to put it on there, but at the same time, you need to be exposed to it. You know what? Maybe I'll put it on as an extra credit problem. That could be the case. All right, here's the remaining two shortcuts for the remaining two cases. What happens if it was tangent secant instead, and what happens if it was cotangent cosecant? They also have trig identities, and like I said, these trig identities show up quite a bit. For secant tangent, this is a very common trig identity for secant and tangent, and this is a very common identity for cotangent cosecant. It's just the same thing rewritten for both of those, by the way. So cotangent is equal to cosecant minus 1. Traditionally, we write it as cosecant is equal to 1 plus cotangent, and secant is equal to 1 plus tangent is the other way that we usually write it. So just a heads up. So get these down, get them written down, and yeah, that's pretty much going to be the other technique. Okay, sorry. I had orange juice this morning, and I just, not to sound gross, but I burped, and a little bit of orange juice came up, and it burned. Oh. I think someone just cursed me and was like, oh yeah, knock me, you can put a problem like this? I hope you choke. And I think I just choked on my orange juice from this morning. Whoever was cursing me, that was a very strong curse. Got me teary-eyed a little bit here. Oh. Yeah. All right. Yeah. So yeah, just get these cases down. Again, if you are still writing them, this is posted online, so you guys can find it. Okay. All right. All right. Let's get that. Last thing for today is going to be part of these techniques for integration, but it's going to be a little bit different. We're going to be combining it with what we learned with derivatives. Again, if you don't have this copied down, if you're watching a video of this, you can pause it, copy it down. If not, and you're watching me live right now, remember, this is all posted online on the OneNote app. So if you're on the Canvas page, you can click on OneNote. This stuff will be there for you. You can take a screenshot of it. You could write it down, whatever you need to do, because I'm about to move on to this last part. Okay, here we go. The last part. The last part we're going to talk about here is going to be the applications applications of integrals. And the easiest application of integrals we're going to talk about is position, velocity, and acceleration. Right? Position, velocity, and acceleration. So if you guys remember, right, position, we use s of t to define it, right? That's what we did for position. And then we found out that velocity had a connection with position, didn't it? How fast something went was dependent on how far it traveled divided by how long it's been traveling for, right? So that's what velocity is. And to find instantaneous velocity, velocity at a particular position that it's at, we realize like, hey, that's just the slope of the tangent line at that point. In other words, it's just the derivative of that, right? Well, now that we know that the integral of a function is basically related to the antiderivative, or in other words, the backward steps of a derivative, I can say then that if I were to take the integral of velocity, the velocity function, I would end up with the position function plus a constant. I would have a function of its position, right? I have a function of its position, dt. Now, that would tell me the function of its position. If I were doing the integral from a to b of v of t dt, that would tell me then, right? It would be, this would be equal to, if I did this evaluation, I would get s of t, but there's no plus c involved. This right here would tell me the total, right? This would be the total displacement. And we'll talk about this word later. It's not the total distance traveled, it's the total displacement, and there is a difference between the two. Total displacement and total distance traveled are almost related, but they're not the same. But the idea is, now we can apply these integrals and we can actually calculate what the function is for position and what the function is for acceleration, for velocity if I was given acceleration, right? Because acceleration, right, we know that that is just equal to the derivative of velocity. So let's take a look at a problem. Let's take a look at a problem here. Let's see here. Do I have a problem set up on hand? No, these are just my annoying ones. Hold on a second. Do I have it? Where are you? Hello? Thought I had you ready to go. Did I not? Shoot, I did not. All right, knock me. Come on now. You know what? We can get it. We can figure this out. So let's say I have here, right? Given. Yeah, why not? Let's say I was given velocity with respect to time is equal to 9t squared plus 4t plus 1, right? Find the position function. I'll give you a second to copy that down there. Given, oh, I should write this down too, the initial condition s of 0 is equal to 3. S of 0 is equal to 3. So I'll give you a second to write that down. Now, you'll see this one and you'll probably say like, these problems are a little bit easier, but that's because the concept is the idea that you can connect velocity with position, you can connect acceleration with velocity and all that good stuff. So I'm making the function a little bit easier to deal with. So when we do the integral, we don't have to deal with U-Substitution or all those trig functions, but most of them we'll deal with them. But this is just an initial one. So find the position function. Position function, remember, s of t is just going to equal to the integral, right, of v of t dt. That's all this is going to be. All right, don't forget the plus c, of course, when you do this. But to find our function completely, we need to plug in our initial condition and find out what c is. Sorry. All right, so let's take a look here. So the position function is going to be equal to the integral of 9t squared plus. Wow, did I put an x there? That should be a t. Sorry. 4t plus 1 dt. Right? The position function is equal to the velocity function, the integral of the velocity function. So let's go ahead and integrate this. What is this going to be? Does anybody know what the integral of 9t squared is? If not, let's do it using the power rule. This is going to be 9 times t to the third over 3 plus 4 times t to the second over 2 plus t, right? Because the integral of 1 is just t, plus c. Cleaning this up, I end up with my position function being 9 and 3 cancel out here. I end up with 3 times t to the third plus 2 times t to the second plus t plus c. Now, this is not your position function done. This is a general solution, right? This is my general solution because of that plus c. How do I get that? How do I solve for plus c? Has anyone been doing the differential equations homework? Has anyone been working on the differential equations homework? How do you find for a plus c? And Monica's saying, plug in the values. Yeah, plug in the values. And you'll say, what values is Monica talking about? And that's the values that Monica is talking about. You could plug in these values here. Now, you'll say here, if you understand this notation, this is saying that when t is equal to 0, s is equal to 3. Right? So you need to make sure you understand that notation, right? This is s of t, right, is equal to some function. So at t equals 0, position is equal to 3. So when does this thing equal to 3? It equals to 3 when this t value is equal to 0. So those zeros cancel out. I'm left with 3 is equal to c. So what's my position function look like? S of t is going to look like 3t cubed plus 2t squared plus t plus 3. That's my position function. That's my position function. Once you find this out, which, by the way, velocity, position, and acceleration is another general favorite for free response questions because they like to break it over into parts. One of the parts might ask you to solve for your position function. It might not look like position. It might look like something else. But just to keep an idea. 2 years ago, there was a problem that didn't deal with velocity. Instead, it dealt with the rate at which sand was being washed up onto a beach. So that was like our velocity function. When you take the integral of that, you could find out how much sand has been washed up on the beach. And that's what this is. This is the how far something traveled, right? The other problem was how much sand got washed on there. It was the same thing, but since they used sand, it screwed up my students. And I realized it was my fault for not preparing them for the fact that they're asking the same thing from this question. They just worded with using sand. And I looked further into this. You know, the AP people are kind of like sick people. I shouldn't say that. This is being recorded. They're kind of interesting people. In the previous years, one of the questions that was on the free response question that had to deal, it was the same idea. It was like, you know, you had velocity, you take the integral of it, you get position, right? So 2 years ago, it was you have the rate at which sand is being washed up on the beach. You integrate that, you find out how much sand ends up on the beach. A couple years before that, I found out from other AP teachers, there was a problem on there that involved with the number of people that go up and down an escalator. So you had the rate at which people were getting on an escalator. You do the integral of that after a certain number of time throughout the day, you could calculate how many people got on an escalator based off of that function. And I was like, huh. And a lot of people got it wrong because it was a weird question of like people getting on an escalator, but they didn't realize all you had to do was just this type of problem. The function might have looked, you know, uglier, but it was the same idea. You take the integral of it and you can get that total thing. And that's an application that you can do with integrals. It's a summation problem. If you have a rate at which something is going at, because velocity, that's all velocity is the rate that something is traveling, right? Those other problems is the rate at which people were adding on to an escalator or rate of which sand is adding on. If you do the integral of that, it's the the summation of the total amount of things that are being added or subtracted, right? Because if you do minus it, you take it away. And that's the thing that most students have trouble seeing, is that when you do these integrals, when you do these crazy techniques to integrate all these things, it's all nice and good, but you need to know how to apply them to the different word problems that are going to show up to that. And I think that's what we're going to practice more eventually. But for right now, that's pretty much the gist of this unit, right? U-substitution, different techniques, and then that's going to be it. I'll have like maybe one position problem on there just to make sure you still remember that position, velocity, and acceleration all have a connection with each other. And also slope fields, right? Slope fields will be on there as well. So you'll have those differential equations, right? So dy dx equaling to like y squared over x. You need to know what that looks like on the slope field. You also need to know how to integrate this or solve for that differential equation. So that's going to be it. I'm going to go ahead and post up your study guide, which will be done on there for a curve, and then your delta math, which will be on there for a curve. And you guys will have until Wednesday midnight to do that, and then your test will be on Thursday. For you juniors, I've been thinking about this while we're working it out. So you seniors will be taking your test in class on Thursday like you normally would. For you juniors, you have the SBAC on both Thursday and Friday. You're just going to have to find another time to come in and make it up. You don't have to come in, I should say. You just, God, I thought I had an idea for this. I'm thinking I'm just going to have it open for the juniors over the weekend, but it's going to be timed just like it would normally. Yeah, I think that's going to be it. It's just going to have to be some time over the weekend for you to do it and catch up on it. Okay? Yeah, I think that's what we're going to have to do. I'll figure that out. I'll let you guys know. But let's go ahead right now and let's get you guys set up, at least so you can do your delta math stuff starting today. Let me go ahead and set up your delta math review for this unit. This, by the way, is unit 6. Almost done. So let's go ahead and create a standard assessment. This is going to be unit 6 review. All right, this is going to be for period 3 and period 4 AB. Let's post this immediately. There's no time limit. Solutions shown. You have access to the delta math videos and hidden after due. That's going to be a yes from me because I don't want you to be able to work on it. Actually, no, you know what? No, you guys can still look at it. Yeah, we'll do that. All right, let's take a look at some skills here. Uncheck all, go to calculus. We're doing integrals, right? Definite integrals. Let's see here. What's some good ones here? Definite integrals with substitution, type 1. Penalty off of 1, but let's go with only 3 problems to practice with there. And then we'll go with a level type 2 right here. Same thing, 1 penalty off if you get it wrong, but we'll go with 2 problems right there. All right, so far we have an estimated time of 17 minutes to do this. Integrals and average rate of change. Calculus, piecewise, integrals of transcendental functions. There we go. We got to do one with exponentials. I'm going to ask for just one of those. Definite integrals of rational functions. We're going to go with 3 of those. Derivatives, integrals of transcendentals. What does that look like? T to the E plus 1 over E. Right, that's not too bad. T to the E. Oh yeah, that should be fine. All right, let's get that in there. Transcendentals. Let's get 2 of those. Not too crazy. And then we have these ones. I had you guys do the particle motion last time, but it like was weird, right? But let's do this one right here. Let's do the rate in, rate out problem. I'm only going to ask you to do one of these. Because, yeah, let's go with that. Units of derivatives, no. Questions? No. Integrally defined functions. Finding functions from integrally defined functions. No. we're not going to do that. I think that's going to be good enough. It should take you about 40 minutes to do. That shouldn't be too bad. I might add on a couple more, but I think that's going to be it for now. I'm going to go ahead and create that assignment so that I must set a due date, of course. So this is going to be due next Wednesday at midnight, 7:59 p.m. And let's go ahead and create that. So that should be up and good to go. I'll put the study guide up for you as well today. And it is 10:37 now, so let's go ahead and let's call it a day there. All right. Have a good weekend, everybody. Stay out of trouble. Stay out of jail. Don't get pregnant. I have office hours today from 1 to 2, and I will be here after school from 3 to 5 if you want to stop by. You can still sign up if you want to. Other than that, have a good weekend. Stay out of trouble. Stay out of jail. Don't get pregnant. Bye, everybody. Bye, Monica. Bye, Emily. Have a good weekend, you too. Bye, David. Bye, Leslie. Bye, Diana. Bye, Angela. Have a nice weekend. Bye, Ava. Bye, Joe.